All right, these are going to be our notes for substitution method. I have printed out copies of this exact set of notes, not filled in. If you have a two-subject notebook already, this is going to be the first page in your two-subject notebook. For those of us that don't have this yet, we're actually just going to glue this page into our notebook so that everything's all organized. So let me give you some time. If you have a notebook already and you want to write this in, we're doing systems of equations and we're doing the substitution method. Today's date is 01/30/25, so go ahead and write that on there. And then we're just going to set up this little table right here, and I'm going to do an example, and then you're going to write out the steps alongside so that you have that to look back at. And I think a lot of this you guys will know from having just kind of practiced some of those problems to start off. So our example is x equals 4y plus 7 and 2x subtract 6y equals 12. So this is a system of equations because we have two equations and two unknowns, and we're trying to find the ordered pair or ordered pairs that are true for both of these equations. So our first step is to isolate a variable in one of the equations In our case, x is already isolated in the first equation. So I'm just going to go ahead and highlight that so you see that x is already by itself. So when I say isolated, I mean I want it on one side by itself. All right. Our second step now is going to be to take this expression that x is equal to and put it in for x in the other equation. So we're going to substitute the expression into the other equation for this variable. And so what that will look like is we'll have 2 times 4y plus 7 subtract 6y equals 12. So notice now we have one equation with only one unknown. So this should result in one equation with one unknown, or one variable, we'll say. All right, now we're going to go ahead and solve. So our next step is to solve the equation. So I'm going to do my distributive property. I get 8y plus 14 subtract 6y equals 12. Since these are on the same side, I combine my like terms. I have 2y plus 14 equals 12. I subtract 14 from both sides. And I get y equals negative. Ooh, I got a different answer. What happened there? Okay, so I get y equals 1, negative 1. Now what I'm going to do is I'm going to take this value of y equals negative 1 and I'm going to substitute it into that first equation that has the variable isolated. So I'm going to have x equals 4 multiplied by negative 1 plus 7, which gives me negative 4 plus 7, which is 3. So my resulting ordered pair is 3, negative 1. And then what I'm going to do is check my answer. So I'm going to go ahead and I'm going to take these values and I'm going to plug them back in to see that they work. So if I have 3 equals 4 times -1 plus 7, -4 plus 7 gives me 3, so that checks because 3 equals 3. If I plug it into the second equation, I have 2 times 3, subtract 6 times -1 should equal 12. 6 plus 6 equals 12, so that checks as well. So that is the solution to my equation. All right, now what we're going to do is just do 2 example problems to make sure we're good. And then look at what infinite and no solution looks like. So again, I look and I say, do I have a variable already isolated? I do. My y variable is completely isolated, so I'm going to take this 6x and I'm going to put it in for y in my second equation. So I'm going to have 2x plus 3 times 6x equals -20. Again, when you replace those variables in, or that expression in, you should now have an equation with only one variable. If you still have 2 variables, you substituted it in for the wrong variable and you need to backtrack a little bit. So now we have 2x plus 18x equals -20. 20x equals -20. So x equals -1. Y equals 6 times -1, which gives me y equal to -6. So I have the ordered pair -1, -6. All right, for this one, my second example, we have 2x plus y equals -2 and 5x plus 3y equals -8. In this situation, notice none of my variables are isolated, so you want to choose a variable where I'm not going to create any fractions. So I'm going to choose to isolate this y because it doesn't have its coefficient is 1, and so I'm not going to have any crazy fractions. And so I'm going to go ahead and I'm going to rewrite this first. Oop, that's not what I want. I have 2x plus y equals -2. I need to subtract 2x from either side, and I'm left with y equals -2x subtract 2. Now I'm going to take this expression and put it in for y in my second equation. So I have 5x plus 3y equals -8. So 5x plus 3 times -2x subtract 2 equals -8. So we have 5x subtract 6x subtract 6 equals -8. -1x subtract equals -8. I add 6 to both sides. I get -1x equals -2. And we result with x equals 2. I then take that 2 and put it in for x in this equation over here. So we have y equals -2 times 2 subtract 2. -4 subtract 2 gives me that -6. So I end up with the ordered pair 2, -6, which I can plug back into my original equations and check to see that they work. For my infinite solutions and my no solutions, for infinite solutions, we're going to follow the exact same process, and I should end up with something like 8 equals 8, or 20 equals 20, 0 equals 0, 2 numbers that are the same that are going to equal each other. And then for no solution, I'll end up with like 3 equals 8, which doesn't work, which is why I write no solution. So if your variables completely go away, that means that you're going to either have an infinite solution or a no solution. So there should be no variables at the end. So go ahead and solve both of those to show that the one on the left is infinite solutions and the one on the right is no solution. All right, guys, you're going to go ahead and work through your homework assignment. In your homework assignment, you're graphing on one side, and then you're doing the exact same problem but using substitution method on the other side. And then that way you can kind of check your answer with the graphing method.